Both of our engines are going to require a minimum valve size of a 202-inch intake and a 160 exhaust. The original heads had a 194 intake with a 150 exhaust. On our application, we decided to use an early full-weight casting. The reason for this decision was because the early castings have more metal in them and they're less susceptible to cracking, so they're more durable. Let's take a few moments and compare our stock head to our reworked stock head. Looking back at the stock head, as you recall, we had our pressed-in rocker arm studs, our stock valve guides. The factory push rod guides are going to be enlarged with a 1/2-inch drill to make them not only longer but wider. Looking at our modified stock head, you can see we've installed the screw-in studs. They're depicted by the hex at their base. This is our aftermarket guide plate, which will locate our push rods more accurately into the rocker arm. And you can see that the valve guide has been machined to accept our positive seal. If you recall, we said we were going to open up the factory rectangular push rod guide with a 1/2-inch drill, and as you can see, we have done so here. This ensures us that our push rod will have adequate clearance to move without contact in the head. If your machine shop is willing, you should request them to surface the entire valve gasket area of the cylinder head as we've done on our head. This will greatly improve valve cover sealing and valve cover gasket life. The reason for going to the 202 and 160 valve combination is to increase flow potential in both intake and exhaust. Taking a look at the stock 194 head with a caliper placed directly below the valve seat, we have this dimension. Comparing it to our modified 202 intake port directly under the valve seat, you'll notice how much larger the opening is. This will result in a lot more flow potential, which will help us achieve much more power in both our engines. Similar gains will be received on the exhaust valve. Let's take a closer, more in-depth look at our modified cylinder head. We arrived at this valve pocket and seat arrangement by first using a 75-degree long blade cutter and opening up to a larger valve size. Afterwards, we took a 45-degree cut, which is represented by this red line, and that will eventually be our actual valve seat. Afterwards, we took a 30-degree cut on top of the seat and a 60-degree cut below the seat to obtain an 80 thousandths width seat that will center itself on our valve. Taking a look at our intake valve, we'll notice that we have a 100 thousandths wide face, and this is a representation of the 80 thousandths wide seat location on the 100 thousandths wide face of this valve. It should be centered. By using the 80 thousandths wide seat on a 100 thousandths wide face of a valve, we'll obtain good sealing, high flow, and great longevity. A few last notes on preparation of the modified stock cylinder head would be to take a sanding roll and lightly polish the combustion chamber. It doesn't have to be mirror smooth, but you want to take out the major coarseness of the stock casting. Also, with a cartridge roll, you want to go down into the bowl of the intake and exhaust ports and finish your blending of all angles. On the intake, you don't want it too smooth. Leave it slightly rough. Similar preparation should be done throughout the length of the intake runner. Once again, don't make it mirror smooth in the intake. A slightly rough finish will give you better flow. On the exhaust, however, you can't polish it enough. If you make the entire exhaust valve pocket and runner polished like a mirror, you can't hurt anything. You should also take the sanding roll and deburr the edge of the combustion chamber to remove hot spots. Deburr the base of the spark plug hole to remove hot spots. And then take a small round file and very carefully round off this area between the intake and exhaust seat where they come together and form a sharp edge. Let's take a look at the features of the bow tie head. Firstly, the bow tie head already comes machined for the 202 and the 1/6 valves. It also comes fully machined for screw-in studs and guide plates, positive valve seals, larger valve springs, features angle plugs, has raised exhaust runners which result in greater exhaust flow potential, and it also has larger volume intake runners which result in greater intake flow. The chambers are also slightly more efficient than the stock chambers, and the deck is made thicker for more durability and to give racers greater potential to modify the heads. These heads for our application need only a minor cleanup. The cleanup consists mostly of removing this little lip and flashing underneath the intake and blending it in. Doing the same with all the sharp edges and areas in the exhaust area and all the way through the port. And as in our street head, we smoothed out the sharp edge between the valve seats, lightly polished the combustion chamber to remove the initial roughness, and we did the same thing throughout the intake port. We deburred the edges of the chamber to relieve hot spots, and we highly polished the exhaust port. In essence, with all the modifications that we've done on our stock head, was to bring it close to the potential of our cleaned up bow tie head. The bow tie head has a lot more potential to be unlocked with further work. For both of our engines, we selected camshafts from Lunati. They have a wide variety of cams to suit most needs. Along with your cam will come a fact sheet. This is this sheet right here. On this side of the sheet and over here, they're giving you all the timing in degrees in relation to crankshaft rotation that the cam is based on, including opening and closing of intake and exhaust lobes, lobe center lines, and lobe separation angles. Down here, they're giving us the lift of the valves, the lift of the cam, duration figures, advertised and at 50 thousandths lift. On this side, they're going to give us recommended lifters, springs, retainers, valve locks. Also, the required installed height of the spring and how many pounds of pressure should have at that height. This is the side of the card we're going to concentrate at this time. We'll get back to this side a little later on. In order to measure the installed height of the spring, first we'll do our valve job, then we'll install the valve, put the retainer with the split locks on and pull them up tight, making sure that the valve is tight against the seat. And then we're going to use a gauge and measure from the bottom of the spring seat to the bottom of the retainer where the spring contacts it. One way of accomplishing this is to use a snap gauge. It's very simple to use. You just place one end against the seat, release the tension up against the retainer, making sure that you keep it square, lock the gauge, and it gives us our distance between the seat and the retainer. Taking the snap gauge, we can transfer this dimension to our spring scale. We just bring the scale down until it contacts the gauge, move our stop down and tighten it, install the spring, bring the lever back down until we've reached our stop, and on the dial, read what tension we have. You can see here we have 100 pounds of tension. Now, looking over to our reference scale, we'll notice that it's at 1 3/4 inches, which is our required installation height. If our installation height was not correct, either too large or too small, it can be corrected by either regrinding the seat or the valve to make the stem longer, which would increase our distance, or if the distance is too great, adding shims beneath the spring until we acquired our proper height and tension. A quick but very important note on retainer installation. Let's take a look at this particular valve assembly. If we notice the split lock halves are touching at one side and have a wide gap at the other side. This is incorrect and could be very costly to your engine. It could produce failure of the valve stem and or retainer and split locks. This is a correctly installed set of split locks. Notice there's a fairly even gap on both sides of the split lock. This will ensure that, one, they stay locked into the retainer, they put even stress load across the tip of the valve, and evenly stress the spring load around the retainer. You should have a minimum of a 10,000ths gap on each side. However, the more equal the gap is, the better off you are. One of the necessary factors in computing our compression ratio is to know the actual chamber volume of the cylinder head. In order to accomplish this, we need a graduated cylinder such as this burette, a suitable fluid, and we need to fill this entire chamber with this fluid to measure the volume. In order to do that, we first must complete our valve job. This will dictate the height of the valves inside the chamber. The valves comprise about 80% of the chamber floor. Approximately every 7,000ths of valve height will equal about 1 cc of chamber volume. Therefore, we must have our valve height set before we make the check. In order to seal the fluid in the chamber, we first applied a layer of grease around the back face of both valves, push them down into place, and that'll seal the valves to the head. Next, we're going to put a thin layer of grease around the chamber, and that will attach and seal a clear plastic plate to the top of the head to seal the top of the chamber. Also notice we have a V-notch in which we'll put the fluid in. Lastly, we'll install a spark plug of the type we're going to run for our application. We have found that by using a little glue gun such as this that's filled with grease, we can easily apply a nice bead of grease around the chamber. This makes it very simple. All I have to do now is press our plate into position, pushing it down lightly until the grease spreads. And open a valve. We've already filled our cylinder, which is 100 cc's, to the top with fluid. And now, as the fluid runs out, fills the chamber, when it's full, we'll turn off our valve and we'll just read wherever the fluid's at, and that will tell us accurately the volume of the chamber. Now, by reading the scale, we'll notice we have 72 cc chambers. This information, along with our engine displacement from the piston and the cylinder, the thickness of our head gasket, and the reliefs in our piston, will allow us to accurately calculate what our compression ratio will be. In the event that you're using a domed piston in your engine, we can accurately determine the displacement of the dome by installing the piston on the rod in the block, rotating the crankshaft until the dome of the piston is below the deck surface of the block, then using a dial indicator or a caliper, measure from the deck surface to the flat part of the top of the piston. Afterwards, we're going to grease seal the whole circumference of the piston and seal it to the cylinder. Attach our CCing plate, like we used on the cylinder head, to the top of the block, fill the whole chamber with measuring fluid, and by using the formula in the chart that we supplied with the tape, we can accurately determine either the displacement of the dome of a dome piston or the amount of volume created by the relief of a flat top piston. We're going to rotate the crankshaft so the piston moves down the bore using a straight edge to make certain that the dome is below the deck surface, and then just go a little bit more. Now we're going to use a dial caliper to measure from the deck surface to the flat part of the top of the piston. And we'll need this dimension later in our formula. Now we have to grease seal the piston to the bore and install the CCing plate to the top of the deck. It's taken 147 cc's to fill the void underneath our plate. With that information, along with the distance we measure from the top of the deck to the top of the piston, using that with our formula chart, we can accurately determine what the piston dome volume was. In order to do this, you want to concentrate on the piston displacement part of your formula. You're going to use the distance we measure from the top of the deck to the top of the piston to represent stroke in that formula. And by using that information along with our fluid measurement of 147 cc's, we can accurately determine the displacement of our piston dome, and with using that information with the rest of our formula, we can accurately determine our compression ratio. One other unique difference of the small block 400 Chevy engine as compared to all other small block Chevy engines are the modifications to the cooling passages within the engine. The 400 has extra water passages which run from the block through the cylinder heads. These are required in order for adequate cooling. Looking at the 400 cylinder head gasket, we'll notice these 6 holes. These holes are not apparent on all other small block gaskets, and also note that they're all placed between adjacent cylinders. When using non-400 cylinder heads such as we are on our engines, these passages must be located and drilled into the cylinder heads. To do them is a very simple process. We need to take the 400 cylinder head gasket and locate it on our head using a 5/16 dowel, or in our case using 2 5/16 drill bits to serve as the alignment pins on the block. This will hold our gasket in proper alignment on the cylinder head. Now what we have to do is center punch the area within these holes and then drill the holes, as you can see on this cylinder head, which has already been modified. We've drilled the 6 holes and we've made them 1/8 inch diameter, which is smaller than what the factory would use in the 400 head, but for our purposes is more than adequate. This will ensure that at low speeds and at idle, we will not risk overheating the cylinders in these areas. Traditionally, aftermarket aluminum intake manifolds have been offered in 2 distinct styles: the open plenum and the split plenum designs. The open plenums were designed primarily for mid-range, upper mid-range, and top-end horsepower. The split plenums were designed for low RPM through mid-range and some upper mid-range power. We're going to use the Performer RPM from Edelbrock, which is a split plenum manifold, on both of our test engines because we have selected camshafts that will run in the RPM ranges of the intake manifold.